In order to get good at this integration by substitution, I'm going to go over a couple more examples with you. And what I look for is a function within this expression that has a derivative that's also there. So if I highlight the sign here and I think about what's the derivative of sine, it's the cosine. So that's a pretty good indication that I would need to make my let u equal sine theta. Then I do the derivative of sine with respect, derivative of u with respect to sine as theta, and I get du by d theta is cos theta. I move the d theta over to the other side, and now I replace everything that I have in here in terms of u. So that means that the e has to stay, but this sine theta can be written as a u, and all of this can be written as du. And now I can easily integrate e to the u plus c, and my last step is to replace the u again. So I've got e, and my original u is sine theta plus c. And you can double check this by taking the derivative, and you should end up with this expression. So let's move on to a second example. In this case, I'm still looking for a derivative and a function. So if I imagine that this is the function, the derivative of that would be 2x. So I'm close to having a 2x here, but not quite. I'm still going to give it a try though. I'm going to let u equal x squared plus 1. Then I take the derivative, which is 2x. I move my dx over, and now I try and replace everything in here with u's. So I've got a u in the denominator because all of this is just u, and in the numerator I've got this expression right there, x dx, which is this piece. So actually what I need to do is get rid of this 1/2 on the right side, and I'm going to write 1/2 du is equal to x dx. Now I can make the replacement for all of this with 1/2 du. And I'm going to put the 2 on the bottom and the du on the top. So I've got integral of 1/2 and then 1 over u du. Just writing it in little pieces so it might be easier for you to see what the original function was. So this is the derivative, which means that the original function must have been the natural log function. So I've got the half and the natural log. I'm going to make sure I take the absolute value, which is x. Going too fast there. I'm going to put this as a u plus c. And now I'm going to replace my u with x squared plus 1. And x squared plus 1 is always positive, so that means I can take off this absolute value. And I get my final answer, which is 1/2 log x squared plus 1 plus c. So moving on to a third example. This time, if you imagine or think about what the derivative is of this function right here, the derivative of inverse tan, it might have been a while since you've seen it, is 1 over 1 plus x squared. So really, I've got the derivative sitting right there. And that tells me that I need to let u equal inverse tan. I take the derivative, which is 1 over 1 plus x squared. I'm going to move the dx over to the other side, and I'm going to write this as 1 plus x squared dx. Now I'm going to replace everything in here with u's. So that means that this here is a u, and this is du. And isn't that an easy integral to take? The integral, just the general power rule in reverse. So it's u squared over 2 plus c. Now plugging in my original u expression, which is arctan, it's squared divided by 2 plus c. So one last example now. Here we go with this one, and I'm going to let I've got a sine here and I've got a cos. So if I let u equal cos x, let's see what happens. So du by dx equals negative sine x. That means du is equal to negative sine x dx. So just moving this over to the other side. All right, now let's see if I can make a replacement for everything. And my replacement, this is going to be u squared. Sine x dx is this piece right here, so I really don't need that negative, so I'm going to move it over to the other side. So negative du equals sine x dx, which means I can now replace sine x dx with a negative du, sorry, there we go. And now the negative is just a constant, and 1 plus u squared, 1 over 1 plus u squared, we've just done that. That's the arctan, or the inverse tan of u plus c. And now I'm going to do my final step, which is to replace the u with my original expression. There we go. End of examples of indefinite integrals using substitution.